Hi everyone, and welcome back to week 15 of the exam countdown from the Maths Tutor. As always, our full members, you have lots of resources online on TheMathsTutor.ie, and if you're not a full member, I've linked two very useful videos in the chat. The first one is a video on graphing sine functions, how to graph sine functions, and the second one is from the exam papers 2016, paper 2, and it's question 8. It's exploring a cosine function. So hopefully you find those of some use. As you can see from the heading, we are jumping straight into trigonometric functions. So just to start us off, we're going to have a very quick look at some basic trig functions, so basic sine and cosine functions. So you'll see here I have two functions drawn. One is a cosine function, one is a sine function. So this one on the left is our sine function, so y is equal to sine x, and this is our regular cos function, y is equal to cos x. You'll see they're quite similar, they have the same kind of shape. But the one big difference is where they begin. So if you look here, the one for sine x begins at the point 0, 0. And that's because if you found the sine of 0, it should give you 0. So you can check that on your calculator. And the cos function starts up here at the point 0, 1. And again, that's because if you found the cos of the angle 0, you will get 1 on your calculator. So that's a nice handy way of remembering it. We talk about the period and the range of the graph. So to start with, the range of each of the graphs, so that's how high it goes on the x and the y axis. The range is always 1 to minus 1, and that is the same with the cosine graph. The range is 1 to minus 1. We also talk about the period of the graph. So when I mention the period of the graph, it's basically when the graph starts to repeat itself. So if we follow the sine graph and we follow all the way around to get back to where we start, we're going right up to this point here. And the period of a sine function is 2 pi or 360 degrees. So depending on whether you're talking degrees or radians. For the cosine function, it's exactly the same. So if we continue on to where the graph begins to repeat itself again, so it begins to repeat itself right there, and that value on your x-axis again is 360 degrees, or if we're talking radians, it is 2 pi. So that's for a regular sine function and for a regular cos function. But we obviously know, and if I just scroll over here to give us a little bit of space, we know that sometimes we can add little bits to our sine and our cos graph. So there's loads of things that we can add. We can add a number at the start. We can add, let's change the color slightly. We can add a number just in front of the sine or the cos graph. This works for both. And sorry, I'm missing one little thing in here. We can also put a number in front of the angle, so we can multiply the angle by a number c as well. So I'm just going to talk you through very briefly what each of these things does. So to the function, so again, this works for sine or a cosine graph, and I'm just looking at sine for now. So to start with, that a, if we add a number at the very start, that's basically going to shift the graph up or down. So depending on whether it's a positive or a negative number. So what do I mean by shifting the graph up or down? Well, if I go back over here, basically it might shift the graph up here. So it'll still stay the exact same shape, and the range and the period won't change unless we change some of the other letters. But it will just shift the graph up, or it might shift the graph down. So it picks up the graph and it moves it up or down. This number here, so if we multiply the graph of sine x or cos x by a number, so b in this case, what that does is it affects the range. So it stretches or it shrinks the graph vertically. Okay, so what I mean by that is, for example, if b was, we'll say if b was a half, for example, what would happen is it would be exactly the same graph, as you can see, but it would only be half the amplitude or half the range. So it would only be going up as far as a half there instead. And vice versa, if your b was 3, it would be 3 times. So it would be stretching the graph vertically if we multiply by a number here in the front. And the last one is this number in front of the angle. So that affects the angle, and that's going to affect the period. So the period is going to be 360 degrees divided by whatever that C is. So if the C is 2, well then the period is 360 over 2, which is 180. So you can see it kind of squashes or stretches the graph horizontally. Okay, and we're going to see that anyway in an exam question that we're going to look at now. But quite important, I suppose, that we have three things that can happen. We can shift the graph up or down, we can stretch or shrink the graph vertically, and we can, by changing this number here, stretch or shrink the graph horizontally as well. Okay, so we're going to have a look at a couple of exam questions today. We're going to start with the sample paper, so the SEC sample paper. It's paper 2 from 2014 and it's question 5. So this is all about exploring a sine graph. So the diagram below shows the graph of the function sine 2x. So that's the graph that we're given. The function is sine 2x. And this line 2y equals 1 is also shown. So before we do anything, I'm just going to take this 2y equals 1 and I'm going to rewrite that, get the y on its own at the left hand side, it's y equals a half. So as you can see there, that line, it's a straight line passing through a half on your y-axis. So part A asks us, on the same diagram above, sketch the graphs of g of x, which is just going to be a regular sine x, and h of x, which is going to be 3 times sine 2x. So if we take g of x, first of all, it's going to be sine of x. So let's have a look at how that differs from this up here. Well, our regular sine x graph is the one that we had drawn up here originally that I've highlighted in green. So it's this one over here that I had highlighted in green. But what sine 2x does, we know from what we've just said, is that changes the period from 360 to 360 over 2. It changes the period to 180. So you can clearly see down here, that graph, it's definitely a sine because it starts at 0, 0, and it begins to repeat itself after 180 degrees or pi in radians. So we're going to draw the exact same shape, exact same amplitude for g of x, but this time the period is going to be 360 degrees as normal. So let's just change the color so we can see it a little bit clearer. And we're basically trying to get the graph to start repeating itself over here at 2 pi, but we're not affecting the amplitude at all. So it can't pass 1 or minus 1. Now, this is just a sketch, so you don't need to be too precise. Basically, what they're going to be looking for in the exam paper or in the marking scheme is that you know that the period begins to repeat itself, or the graph begins to repeat itself after 2 pi, but the amplitude in this one is unaffected. Okay, so in purple there, I have drawn my g of x, which is just the sine x graph. Okay, just going to change up the color so that we can see it a little bit clearer. I'll go for green. So this time my h of x is 3 times the sine of 2x. So the sine 2x tells me that the period is going to be the same as the graph that was drawn already. It's going to be a period of 180. But this 3, remember, that affects the amplitude. So that's going to stretch it horizontally. So what we want in green is we want the exact same period, but we want to reach an amplitude of 3. So we're following the exact same shape and we're going back down to 3 and we're repeating ourselves after pi, or after 180 degrees. So again, something along those lines. It's not exactly accurate, but what we're looking for is, number 1, it starts here at 0, 0. Number 2, it repeats itself after pi. And number 3, the amplitude up here is stretched to 3 and minus 3, or your range is stretched to 3 and minus 3. Okay, it asks me to indicate clearly which is G and which is H. So if you like, you could color code those to make it stand out a little bit better. Part B, find the coordinates of the point P on the diagram. So if we just look back at where the point P was to start with, it's right there, so that point there. And you can see it's where your function f of x meets that line there which we know as y equals a half or 2y equals 1. So what we're interested in for part B is where my function y equals sine 2x is equal to the function y equals a half. In other words, it's where sine 2x is equal to a half. So this is back to our just our regular trigonometric equations that we're going to solve, and hopefully we remember that we start by drawing our ACTS, our unit circle. Now, where we're interested in, if we have a look, we're interested in where sine is, this is a positive number here, so sine is going to be positive in that quadrant and in that quadrant there, and we're going to find our reference angle, which is going to be the sine inverse of a half. So the sine inverse of a half, and that will give me a reference angle of pi over 6. So we're in radians. Again, it hasn't really specified here, but I'm going at radians because in the diagram up here, the angles were in radians. So that's why I'm sticking with radians. So we're looking at pi over 6 in this quadrant. Well, that's just going to be pi over 6. Pi over 6 in this quadrant, that's going to come from 180 degrees or pi radians minus our pi over 6. So my two angles for 2x, one of them is going to be pi over 6 and the other one is going to be, that should give me 5 pi over 6. But don't forget, we're going to add on our 2n pi because as you can see from the graph up here, it continues and it continuously repeats itself, the sine function. So we're adding on 2 pi n times, as many times as we want. So to get our x on its own, which is what we're looking for the x coordinate and the y coordinate, we're going to divide across by 2. So we're getting x is equal to pi over 12 plus n pi. And for here, we're getting 5 pi over 12 plus n pi. And what we're going to start doing, we're going to start subbing in our values of n. When we start is n equals 0. And we continue. But if we just look back at our diagram, now it's a little bit tricky to see because we've so much in on the diagram. But I'm just going to mark out all the points on that graph where the two functions are equal. So our first point is going to be right there. The two functions meet there for the second time, there for the third time, and P is actually the fourth time that they meet. So when I go back here, when I let n equal 0, I get x is equal to pi over 12, and I get x is equal to 5 pi over 12. So that's the first two times they meet. So I have to continue. I have to go to n equals 1. And when I do that, when I sub n equals 1 back in up here, I get x is equal to 13 pi over 12. 13 pi over 12. And x is equal to 17 pi over 12. So this is the first time they meet, second, third, and the fourth time they meet is when we are interested in. So our coordinates of that point P are going to be, well, our x coordinate is 17 pi over 12. And if we look back at our diagram, the y coordinate of that point P, because it's on this line where y is equal to a half, well, the y coordinate at every point on that line is going to be a half. So that's where our x value comes from solving a regular trigonometric equation, and our y value comes from every single point on that line has y-axis or has a y coordinate of 12. Okay, so that's just having a quick look, and it really, I think, hits home what the different numbers in front of the angle and the different numbers in front of the sine or the cos function, what they actually look like on a graph. So it's quite a good one to try. Okay, so we're also going to have a look at today from 2019 paper 1, we're going to have a look at question 8, and it's a little bit of everything. You've kind of functions in here, you have a trig function, namely, so we have a cos function here, but we also have a little bit of differentiation, a little bit of calculus thrown in here as well, which is nice. So, the weekly revenue produced by a company manufacturing air conditioning units is seasonal. The revenue can be approximated by that function, and it's telling you that time, T, is the number of weeks measured from the beginning of July, and the angle is in radians. So that's quite important here. you need to make sure that your calculator is in radians so that every answer we get is in the right unit, I suppose. So the first question, nice and easy, find the revenue or the approximate revenue produced 20 weeks after the beginning of July and give your answer correct to the nearest euro. So we were told that T was the number of weeks after the beginning of July. So this time we're basically taking our function and we're replacing T with 20. So it becomes R of 20 is equal to 22,500 times the cos of pi over 26. T becomes 20 plus 37,500. So you can see there the only thing that has changed is our T has become 20. And that's just going straight into your calculator. And what we should be getting to the nearest euro is 20,659. And again, correct to the nearest euro gets us our full marks there. Okay, again, make sure that your calculator is in radians when you're putting this function into it. So part 2, find the two values of the time t. So we're expecting two answers within the first 52 weeks when the revenue is approximately 26,250. So we're looking for t. T is our question mark, if you like, and they're telling me that this is my revenue. So I'm taking my function from the question, and that was 22,000. So our R of t, our revenue, was 22,500 times the cos of pi over 26t plus 37,500, okay? And they're telling me that that's equal to 26,250 for this part B. So our job is to try solve this equation to find that t in there. So to get that t on its own, we're going to solve the equation, but we're expecting two answers. So a couple of things to do. This 37,500 is added at the left. So what we're going to do is we're going to subtract 37,500 from both sides. And that should give me 22,500 times the cos of pi over 26t equals 2 minus 11,500. So we subtract 37,500 from both sides. We're also going to divide both sides by this 22,500. So that should leave you with cos of pi over 26t is equal to minus a half. So when we divide this by 22,500, it leaves me with minus a half. Okay, so we're down to cos of an angle is equal to minus a half. Now remember they said up here we need two values. So we're actually going to, go back to our ACTS unit circle like we had in the last question. And this time we're interested in where cos is a negative answer. So cos is going to be negative in the S quadrant and in the T quadrant. So our two answers, once we find our reference angle, our two answers are going to come from those two quadrants. So to find our reference angle, we're going to find the cos inverse of a half. So we ignore the sine because we've catered for the sine by using our unit circle up here. And when we get the cos inverse of a half, that gives us in radians again, our calculation is in radians, it gives us pi over 3. So let's think about it like we did in the last one. That's going to be pi over 3 in this quadrant. So that's pi minus pi over 3. And it's going to be pi over 3 in this quadrant. So that's going to be pi plus pi over 3. So my two angles, and remember this was my angle here, pi over 26 times t. So pi over 26 times t is going to be equal to, well, one answer is going to come from 2 pi over 3. So that's from here. And then my other answer is going to come from here, and that's 4 pi over 3. So when we solve for t here, we divide by pi over 26. That gives us t is 52 over 3. And when we solve here, dividing by pi over 26 again, we're getting 104 over 3. And remember, it's weeks. Our time is in weeks. Okay, so what you're looking at there, 52 over 3 is about 17.3 weeks. and 104 over 3 is about 34.6 weeks, again after or from the beginning of July we're talking about. So it's quite important there that we get our two answers. Now, looking at the marking scheme, even if you just went ahead and got your one answer, so most people will be able to get to, I suppose, this point here and get one answer, you're getting 4 out of 5 marks there, so you're getting high partial credit for just getting the one answer. Okay, so part C then, we're on to a little bit of differentiation, and we're looking for r dash t, which is the derivative of this function. So they're just restating the function here for you. So first of all, when we look at it, we definitely know that we're going to be using chain rule because it's not just a regular t in here, it's a function of t, so it's a function within the cos function here. So starting off, r dash t, when we differentiate the 22,500, that's just a constant out the front, so that stays as 22,500. When we differentiate the cos, that changes to minus sine. So I'm going to put the minus out the front, sine, and the angle never changes. So that's pi over 26t again. And don't forget, you also need to differentiate what's inside here, so the inner function. So when I differentiate that, I get pi over 26. So this differentiated gives me pi over 26, because pi over 26 is just a constant hanging on the front of the t, so the t just disappears. And obviously when I differentiate 37,500, that goes to 0. Okay, so that's the differentiation pretty much done. We're just going to tidy it up a little bit. We're going to bring the constants all to the front and multiply by each other. So that's going to give me minus 22,500 pi with 26 on the bottom times the sine of pi over 26t. And the angle, remember, never changes. So when you differentiate or when you integrate, your angle should never change. The angle should not be changed, but remember the angle does need to be differentiated. So that's what we were doing here. Okay, and that's your derivative. For part D, use calculus to show that the revenue is increasing 30 weeks after the beginning of July. So we basically want to show that the slope, in other words, the derivative, is positive. It's increasing 30 weeks after the beginning of July. So let's just make a note of that for ourselves. If it's increasing, so that means it's basically going uphill from left to right. So therefore your slope, and we know that the slope is the same thing as the derivative, the slope or the derivative has to be positive. It has to be greater than 0. And when? Well, 30 weeks after the beginning of July. So in other words, we're going to use our derivative, r dash t, but instead of time, we're putting 30 in here instead. So taking our answer from the previous part, that was minus 22,500 pi over 26 times the sine of pi over 26, and this time our time is 30. Let me just close that bracket there. So again, just to go through that again, if it's increasing, that means the slope is going to be positive. So the slope was what we, or the derivative was what we found up here in part C, and all we're doing is we're replacing the t with a 30. And again, make sure your calculator is in radians, as it should be from the start of the question. When you plug this into your calculator, you should be getting 402.16 or something similar, which all we care about is that it's positive. Okay, so therefore, to answer the question, it's increasing 30 weeks after the beginning of July. So after the start of July. So make sure that you're actually concluding, you're actually answering the question. You don't just assume that by finishing it and doing it here and getting a positive answer that the examiner knows what you're doing. You need to show your work and make sure that you're concluding with your answer. Okay? And the last one then is part E. Find a value for the time within the first 52 weeks. So time is what we're looking for when the revenue is at a minimum, and use your second derivative to verify your answer. So to get our full marks, we have to use our second derivative. The word that jumps out at me there is minimum. And we know straight away when we see max or minimum, at a max or at a min, the first derivative is equal to 0. Okay, so at a min, the first derivative is equal to 0, and we're picking up marks for doing that. So we are writing down our first derivative, so that's our answer from part C. That's minus 22,500 pi over 26 times the sine of pi over 26 times t, and we're letting that equal to 0. So the first thing that we're doing, this is basically in the way. It's multiplying, so we're going to divide both sides by minus 22,500 pi over 26. But when I do that over here, I still get 0. So I'm left with sine of pi over 26t is equal to 0. Now, what we could do here is we can go with our ACTS unit circle, as we've done before, and what we'll end up doing is we'll end up getting a max and a min, okay, and then we'll use our second derivative to verify our answer to check which is the max or the min. So we are interested in where sine is equal to 0 in this case. So there are very special points here. There's one there, and there's the other point there. That's where our sine is equal to 0. So in other words, at 0 degrees, or at 180 degrees, or 0 radians and pi radians. So if you like, my reference angle is sine inverse of 0. So that's going to give me 0. So my angles, my answers are going to be pi over 26t is either going to be 0, like I said from here, or pi over 26t is equal to pi because we're in radians, and that's my answer from here. So solving for t here, we're getting 0. And for t here, what you should get is 26. So it's going to be pi divided by pi over 26. So we're getting two answers. One, of course, is a max. One is a min. We're not sure which is which. So we'll go and we'll find our second derivative to work that out. So our r double dash t, or our second derivative. Remember, what are we differentiating? Well, we're differentiating the first derivative, which was this up here. So again, when I differentiate that constant out the front, that's going to stay as it is, minus 22,500 pi over 26. When I differentiate sine, sine is going to change back to cos. Angle never changes, so that stays as pi over 26t. But remember, we have to differentiate the angle, just like we did in the first derivative in part C, and that's going to be pi over 26 again. Okay, and all that we're doing is we're subbing in both the 0, so both my answer from here and my 26, and what we're looking for is, at a minimum, we're looking for a positive second derivative. Okay, so at a minimum, our r double dash t is always going to be positive. So what we do is we take our 0 and we take our 26 and we sub in to our second derivative. Now, look, I know it's going to be 26, so I'm just going to sub in 26 and show you what we get. You can obviously also try sub in 0, but you should be getting a negative answer, and that tells you that it's a maximum point. So all I'm doing is I'm replacing that t, that's right there, with a pi over 26. It might not be any harm when you're putting this into the calculator, maybe just to do it slightly in a couple of different parts, I suppose. But I suppose if you look here, your 26 on the bottom and the top will cancel, so that might make it a little bit easier. But if you like, put this part in first, then put this part in, and then put this part in at the end. But in short, you end up getting a positive answer, so you get something like 104.56, which we know is positive. So therefore, your t equals 26 is when your minimum revenue occurs. Like I said, if you want, go back and throw your 0 in here, and that should give you a negative answer, which shows that it is a maximum point. Okay, so what we've done there, I suppose the start of that question was more our trig functions and looking at a cos function, and in part B there and in part D we were solving trig equations. And going back to that really good question from 2014 sample paper 2. That's a really good question to get you thinking in terms of what a sine graph looks like when we do some transformations on it. But like I said, there are two really good videos in the chat for you there. The first one on graphing the sine functions, and the second there on looking at a cosine function from 2016 paper 2. Okay, thank you guys.